Every 5 seconds, a 40-gram mass on a spring oscillates 8 times, okay? Careful there. Did they give us the period? Is period 5 seconds? That's the time for 8 oscillations, okay? And so the first thing, and I know that it's part B, but we can go in and solve for period. Period is how many seconds for one oscillation or cycle. If you want to view an oscillation as a cycle, that's fine. It's how many seconds per one cycle. But we have 5 seconds for 8 oscillations. And so simplify that 5/8 and we get, is it 0.6? 0.625 seconds. Okay, so they don't always directly give you period, okay? And it's not just a matter of, oh, I got to convert minutes to seconds. Maybe that happens in the future. But here, they give you like a collective. And y'all, this is real life lab. Do y'all remember the flying pig lab? When we went out in the hallway and we had the flying pigs? I didn't tell you time 1 circle. I said time 3, time 5, right? And simplify it down to 1. Okay. Find the frequency. Now that we know the period, how do we find the frequency? Inverse, okay? And by the way, let's forget that for a second. Let's define frequency. Can we base it on the definition? What's the defining equation, if you will, for frequency? It's not the timing of one circle or one cycle. It's how many cycles per second or oscillations per second. And so using the numbers in the problem, you had 8 oscillations in 5 seconds. Can we reduce it to 1 second? 8/5 is 1.6. So 1.6 oscillations per second would be an acceptable unit. Or who remembers another official AP, or not AP, SI unit for frequency? Hertz, okay? And so your answer for frequency is 1.6 hertz. And then they gave us the mass. We did not need mass for frequency and period here. Now the period and the mass both do appear in our period of a spring equation, and that's what we're going to use now to find the spring constant. And so we had Ts equals 2 pi times the square root of m over k. We're trying to isolate k. Be very careful here. I'm not going to start with numbers. I'm going to actually do the algebra with the variables, because guess what? On the May 12th exam, most of your algebra is going to be with variables, not necessarily numbers. And so notice where k is. It's in the denominator. It's under a square root. Be careful. This is where a lot of students make algebra mistakes. And so let's start isolating k. What could we do? Step 1. Solve for k. Divide both sides by 2 pi. And so I can say Ts divided by 2 pi equals square root m over k. Still trying to isolate k. What could be our next step? Square both sides. And so if I square the right-hand side, what happens? The square root goes away, right? Now here's where some students mess up. When you square the right, you got to square the left. So t squared, that's true. 2 pi squared, wait, did I just square 2 pi or did I just square pi? Depends if you have parentheses or not, right? And so I don't have parentheses, so you want to make sure you square everybody, okay? A lot of people forget to square the 2. They let it become, we say 2 pi squared, but either put your 2 pi in parentheses and square the whole collective, or square the 2, square the pi. Good? Okay. And then what would we get? We get t squared over 4 pi squared, I'm going to go with, equals m over k. Still trying to isolate k, so the square root's gone, but it's in the denominator. What do we do to solve for k? Cross multiply or switch the diagonals we've talked about in the past, right? And so we would get k over 4 pi squared equals m over t squared. And then multiply both sides by that 4 pi squared. So k equals m 4 pi squared over t squared. Yes. So if it was in variable form, this is the answer. But we do know the mass, and now we know the period, so we can actually plug the numbers in. So our mass is what? Is it 40? I would convert ahead of time. Don't convert at the end. To me, it's harder, even with squares and square roots. Sometimes it's more challenging. And so 40 grams is 0.04. Kilo is 3 places. And so I'm going to use 0.04 in my spring constant calculation. And then 4 pi squared. And for pi, you can use the button for pi, or you can just do 3.14. Over period we had as 0.625. Don't forget to square it. And so let's work it out. Hopefully you got about 4. Yeah. And the SI unit for spring constant is newtons per meter. Okay. All right. This would be the same steps you take for a pendulum if you were solving for G, right? G is the denominator variable in that one. So it's the same steps. Be careful. And then last one here, find D, the magnitude of the acceleration when it's stretched 5 centimeters. And so we know the stretch distance. Now we know the spring constant, and we're looking for acceleration. And so it's not necessarily a max. We don't know if this 5 centimeters is a maximum stretch or not. But at this point, what can we do to get that acceleration? F net. Okay. Now we don't know if it's vertical or horizontal, correct? It doesn't tell us if it's vertical or horizontal, but the acceleration due to the spring is the only thing that's changing here. And so we'll look at it as our MA equals K delta X. Oh, careful, careful. Don't miss this one. 5 what? Centimeters. What do we want it to be in? Meters. So centi is how many decimal places? 2. And so it would be a distance of 0.05 meters. So we know the mass, 0.04. We're solving for the acceleration. Spring constant, 4. And then the displacement, 0.05. And what do we get? Do we get 5? Yeah, we get an even 5. And that would be meters per second squared. Again, we don't know if it's the maximum, but it is at this point. Good? So to me, the big difference in this problem was how they gave us the information for period and frequency. They gave us multiple oscillations and we had to reduce. And then some practice with the algebra of solving for a denominator under the square root. All right, let's do the next one. A 20 kilogram boy swings on a 3 meter long rope. So here we're headed back to the pendulum. And it says, if his 30 kilogram older sister, by the way, does age matter? Does it matter that the sister's older? No. Instead, swings from the same 3 meter rope, how will her frequency compare? And so hopefully with pendulums, with simple harmonic motion, that swinging back and forth, you gotta somehow consider this equation. Again, age or time is not in that equation. Length is, wait a second, where's mass? Does mass affect the period of a pendulum? No. So if her rope, if she's on the same 3 meter swing on the same planet is the implication, then how does her period compare? Same. How does frequency compare? Same. And so if it's the same length, same. So mainly just a concept there, not really a calculation. We could calculate the period and frequency, but they were just doing a comparison. And the last one on page 2, when a mass M hangs from a spring, so we're headed back to a spring. By the way, I was looking around my equipment for a spring. I don't know where they are. They're here somewhere. I don't know where they are. I'll keep trying to find one. But hopefully you are familiar with springs, right? Okay. So it's got a particular spring constant. And when you attach this single mass, it's going to stretch a single distance. Okay, X. If you replace that single mass with a double mass, how far does it stretch from equilibrium? And so let me kind of draw a little picture here. They're talking about hanging. So maybe our spring is attached to the ceiling. So there's our spring. Now let's put a single mass. Maybe it stretches it a little bit, right? What if I put a double mass on the same spring? And note, we're just hanging here. It's just hanging at equilibrium, right? And so if it's just hanging there, do we have an oscillation? Is it oscillating? No, it's literally just hanging there, so it's motionless. And so what would the net force be on the object? 0. We haven't drawn a force diagram in a while, so can we draw one? With our single mass, doesn't it have weight? And if it's all balanced, then the spring force should be equal to Fg. Now, what happens when you have a double mass just hanging? Aren't we still going to be in equilibrium? And hopefully you know that a bigger mass is going to stretch it further, right? Hopefully that makes sense. Now, how proportional, we'll figure out. But if I have a much bigger weight, it still has to equal the spring force. It's just going to increase the spring force. Moral of the story, we're going to use that Fs equals Fg. And so Hooke's law, Kx equals Fg equals what? It's been a while. Say again, mg. K is going to be the same. They didn't change the spring. Gravity is going to be the same. So what happens when we increase the mass? We'll get a bigger stretch. Specifically, if I double the mass, what kind of stretch am I going to get? For it to remain in equilibrium, it's got to be a double. And so we'll get double the original stretch. If it was triple mass, we'd get a triple stretch. All right. Part 2, reset back to normal. Now, what if K was twice as big, twice as much? So we take a weak spring and then we double the strength, right? Remember, spring constant tells us how weak or how strong the spring is. How much would it stretch from equilibrium? And so it's still just going to hang there. We're still going to use this Fs equals mg, but now, or I'm sorry, Kx equals mg. Now we're not changing the mass, but we're going to increase K. To keep the same equality for the weight of the object, what has to be true about my distance, my stretch distance? It has to be less, and specifically, if you double K, you would get half the distance. So final answer would be half the original stretch. Good there? Okay. Questions on this page, page 2, before we move on? All right, let's head to page 3. Page 3 has a multi-solve. So this is going to be, a free response, not necessarily that you'll see one exactly like this. Calculate, calculate, calculate. On the AP exam, maybe there's one calculation problem and then some proportions. Maybe there's a graph drawing. Maybe there's an explanation. Okay. But this one, we do have a lot of calculation. All right. And there's no picture, so I'm going to try my best. I messed up the picture in second period, so hopefully I can get it right this period. We're going to draw a picture in that top margin, because if you're like me, pictures help. It says a 3 kilogram block is dropped from a height of 0.8 meters, and it really, to be clear, it should say 0.8 meters above the spring, because I'm going to show the spring on a table. It's not 0.8 meters above the table. We'll assume, and the key aligns with this, 0.8 above the spring. And the spring has a constant of 100 newtons per meter. The block sticks to the spring. So maybe there's putty, Velcro, some kind of sticky something. And the two oscillate. So does it start out oscillating? No. Is it going to end up oscillating? Yes. But initially, we just got, here's our table. Here's our spring. The block, and by the way, my drawings are not drawn to scale. I apologize, okay? So it's not going to be, don't get out a ruler and measure this for accuracy. But we'll release this object from rest, dropped, right? Free fall. And it's going to fall a distance of 0.8 meters. And then maybe there's like a platform on the spring. I'm going to use that for like measurement purposes. We've got a very light platform on the spring. In the beginning, there's no oscillation, no period. Everybody's just chilling, but you have a height. Think back to January. What's true about our object spring earth system at this point? What do we have? There's a height above the spring. We got potential energy, gravitational potential energy, right? A maximum. No kinetic, because you start out at rest. No elastic potential, because it's not compressed yet, right? And then sometime in the future, and I'm going to leave a little space, okay? Leave a little space. But sometime in the future, we're going to have a max compression. This should sound familiar. We did this already, this portion, back in energy. And so if this is a maximum compression, it's the lowest point of the path. We can actually call this our 0 meters. Oh, let me put that on the other side. Or here. We'll do this. Everybody agree? So if this is our lowest point, we have 0 meters. How much gravitational potential do we have? 0. We come to a split-second stop. No kinetic. So where'd all our potential gravitational energy go? It's now in the form of spring or elastic. Yeah. So this conversion of energy. Well, what happens in the middle-ish, not dead center, but middle-ish? Well, there's a special location, right? Equilibrium. Now, here's where I messed up my original picture last period. It's not in the middle. Are these 2 locations that I've identified for the platform, are those going to be my high point, low point of oscillation? No, maybe sometime in the future when it sticks on the platform and oscillates back and forth, maybe sometime in the future it goes higher, right? Oop, there's our platform. So maybe this is the peak of the oscillation. Okay. Somewhere in between here is equilibrium. Here's a user-friendly way to find your equilibrium. Isn't it true that if you just sit the block on the spring, it'll rest at equilibrium? So that's the picture I'm going to squeeze in between here. If we just sit it on the platform, this is our equilibrium. Now, once it oscillates, it's going to oscillate about that point. Okay. But if you just sit it here, that's your equilibrium place. Everybody good? Okay. I'm trying to be careful with the drawings because we're going to have 3 different distances that we're talking about. And hopefully I've done it well enough to make sense. And so our oscillation is on the right-hand side. So it's going to go up, it's going to go down, it's going to go up, it's going to go down, back and forth, back and forth, back and forth. Okay. What is the maximum compression of the spring? And so maximum compression, well, that's when I had maximum elastic potential energy. Where did all that energy come from? Well, we started with a maximum gravitational potential energy. This is old. And so 1/2 kx squared, and this is a maximum, equals that mgh, if you want to call that a maximum. Now it's actually kind of generic there. mgh, that's just the equation. Would we just put in 0.8? Well, it's a height change from the very beginning to the very end. Notice in our picture, the very beginning to our 0 point, this is our H max. It's 0.8 plus this maximum compression. Agreed? Because it's a vertical setup, your compression is also a height. And so down below, I'm going to plug in for mgh, I'm going to say mg 0.8 plus that x max. Delta x max, same thing. Okay. Notice I've got x max on both sides. Is it going to cancel? No. So this is the situation where it doesn't cancel because we've got that 0.8 plus, right? So later we'll end up distributing, but x does not cancel. In fact, mass doesn't cancel, nothing cancels. And so let's start plugging in some numbers. It would be too hard, I think, variable wise to solve for X max here. And so we'll simplify with some numbers. Spring constant they gave us was 100. We're trying to find that X max squared on the left. Mass is 3. Gravity, I'll use 10. And we got that 0.8 plus X max. So that 3 times 10, 30, we got to distribute to the 0.8 and X. And so let me carry over here. We'll get 50 X max squared. And then 30 times 0.8. What's 30 times 0.8? 4/5 of 30? It's like 24. Plus, and we'd have 30 times that X max. Again, X does not cancel, but what do we notice? It's quadratic. We've got X squared, we've got X on its own, and then we've got no X. So this is the setup for quadratic. And just a reminder, AP would probably give you the max compression and have you solve for height. You can do that without quadratic, okay? And so it's not that we did this on purpose, it's just the way it is, but we got to do the quadratic. And so I'm going to set it equal to 0. And so for right now, if you know how to do it in the calculator, either graphically, equation, or you can start singing your song. Y'all are so lucky. I never learned a song. Plus, I mess lyrics up all the time. I'm the one that y'all don't even know who Tony Danza is, do you? No. I know. Or yeah, not my generation for sure. The Elton John song, Hold Me Closer, Tiny Dancer. Yeah, I was the one that thought it was Tony Danza because Tony Danza is an actor of mine. Who's the boss? He was the boss. Okay. So I get a positive and negative number. Now think about what we're solving for. You know, back with projectiles, when we did quadratic, we said, oh, we're not going to use negative time. Time can't be negative, right? Here with velocity, we said, ooh, it could be positive or negative. This is a distance above our low point. And so we don't want to use the negative number. And so I get 1.055 meters. Okay. And again, don't lose sleep over quadratic. You're not going to have to do it on the AP exam. Okay. Everybody good on that one? Technically, that's old stuff, right? Conservation of energy. B, how far, if any, is the spring compressed when the block has its greatest speed? Now, this is actually kind of using code words for us. That greatest speed, a lot of people will think, oh, it has the greatest speed before it hits the platform, before it hits the spring. But actually, that's incorrect. It's going to speed up until the spring force is greater than the gravitational force. What point in the oscillation, or maybe it's not oscillating at all, at what point does the spring force equal the gravitational force? Equilibrium. And so we're going to look at equilibrium for the Vmax. Now we're not solving for Vmax until the next question, but that's telling us where to look, okay? It's not just free fall right before it hits the spring. And so at equilibrium, this is where, and we did it on the other page, the two forces equal each other. And so Kx equals mg. Now the x is not the maximum distance. We're solving for the compression from where it started to equilibrium. And so K is 100. We're solving for x, and this is the to equilibrium. And then mass, was it 3? Yes. And so I think we get, is it 0.3 meters? Everybody good? Now, before we move on, I'm going to go put these on my picture and hopefully, fingers crossed, not that it's drawn to scale, but that it makes a little sense. And so up on my picture, the full compression, maybe I change colors. And so the 0.3 that we just found is right here in green, if you can see. It's from where the platform started to equilibrium. So that's how much it's going to compress just based on the weight alone. The 0.055 is going to be that X maximum from very beginning to the very end. And that's going to be still in green here. I just need to draw bigger. It's very cluttered. And so that's from the top of the platform to our 0 point. Everybody good? Okay. The next question, part C, what is the maximum speed? Okay, so now we're actually solving for that maximum speed. We know it's happening at equilibrium. That's what we just said in part B, but now we got to figure it out. Now, some of you may be thinking, oh, we did Vmax equals A omega yesterday, yes? Well, I don't know amplitude yet, and I don't know angular velocity yet. We can actually do this. This will work. Or if you're like, oh, can't kinetic energy max? Can't we do energy? Yes, you can. So I'm going to embrace the new. We've spent a lot of time with conservation of energy. The key has both solutions. So if you want to try conservation of energy later and check, you should get the same answer. But I'm going to embrace the new equation because the more we use it, the more we know it, right? And so amplitude, they actually, if we fast forward to part E, we can go solve for the amplitude. And so it's from your compression to the equilibrium. If we go back up to the picture, I think it'll work. That's this distance. Okay, eventually we'll have the same amplitude when it oscillates above the equilibrium, but to the lowest point, going from that lowest point up to the equilibrium location. So how are we going to find the amplitude? I know the maximum, the full distance. I know that little compression to the equilibrium, but it would just be those two numbers subtracted, yeah. And so down here, it's going to be that full compression or max compression minus the distance to equilibrium, and that'll equal our amplitude. So the 1.055 from part A minus the 0.3 in part B So the intent was to use energy, but if you do the new equation, we got to find the amplitude now. And so up in part C, now we know the amplitude. Now we just need omega. Who remembers the new equation? We derived it last class for omega. Angular speed, angular velocity. For a spring. Exactly. And so when we set it equal to the period of a spring, right? Period equals period. This is what, remains. And so they do give us the spring constant and the mass. And so omega, low battery, somebody calculate. I got 5.77 radians per second. And so now we can plug that in and then final solve. So times 0.755. And I get 4.36 meters per second. Good on that? And so challenge, try conservation of energy. See if you get the same thing, okay? All right, D, at what frequency does the block oscillate? So they don't give us how many oscillations and what amount of time, but we did just solve for omega. And so last class we saw period equals 1 over F, but it also equals 2 pi over omega. Both of those are on the formula chart. What if we just look at the last two pieces? Can we cross multiply and isolate frequency? We should get frequency equals omega over 2 pi. Omega, angular speed, we already found 5.77. Now here's where I would warn you with the calculator. Dividing by 2 pi, some calculators divide by 2, and then it interprets your intent of the pi in the numerator. So be careful, use parentheses, or you know what 2 times 3.14 is. What is it? 6.28. And I get 0.92. An SI unit for frequency we said was hertz. But true story, if you want to find the period and then find the frequency, you can, okay? All right, I think one more calculation and then some concept questions. F, what is the magnitude of the maximum acceleration during one cycle? So that A max, well, we had a derived equation from last time. Hopefully this looks familiar. Now that we know amplitude, 0.755, omega, 5.77. All those 5s and 7s, hopefully I type it in right. Y'all are calculating with me, yes? Sometimes I say 5.7 and then I calculate 75. So I get 25.14 if you want. And that should come out meters per second squared. Good deal. Okay, so lots of calculations there. Let's take a break from that and do some concept questions. Now, imagine the mass of the block is only 1 kilogram. So we decreased the mass, right? How would your prior answers have changed? So it's A, B, C, D. We're just comparing the new answers for up above A, B, C, D. Will it increase, decrease, stay the same? Explain. I don't think I have enough room to do like 4 complete sentences, but always relate it back to a physics concept, back to a law, an equation when you're explaining. So I'll kind of put it in symbol form for room reasons. And so A had us solve for that X maximum. So I'm going to scroll back up to part A. Notice where you have mass. So it was our conservation of energy. The more, I'm sorry, not more, less mass. If you have less mass, isn't it all going to start with less potential energy? And then you'll have less elastic potential energy? Yes. If that's true, how much will it compress? Will it compress the same, decrease, or increase? It'll decrease, right? Less. And so it should go down. Now my symbolic explanation, if I have less mass, I have less gravitational potential energy, which means I'll have less elastic potential energy, which means it will compress less. Again, on AP exam, 1 sentence. I wouldn't totally do symbolic. That's kind of a gamble. I don't want to say I have a downward mass. Hopefully y'all are listening as well as looking. Okay. What about B? B, we solve for X of the equilibrium. I'm going to scroll back up. B, we used Hooke's law, that equilibrium of forces, right? And so notice mass is there. If we have a smaller mass, we'll have less weight. There's going to be less spring force. And with the same gravity and spring constant, how much is it going to stretch? Or compress, sorry. More or less or same? Less. So my quick explanation, a smaller mass means I have less weight, which means I have less spring force. And so it'll compress less. Okay. C can be a little tricky. If we'd done energy, I think it would have been quicker to get, but just work with me here. C, we found the maximum speed. It depended on omega. Omega depended on mass, but look at amplitude. How did we find amplitude? It was based on our answers to A and C, right? And so if I have smaller measurements, okay, and we don't have numbers here, we could recalculate this and prove it with the numbers, but we're going to have a smaller amplitude. And what about omega? If you have a smaller mass, be careful here, there's also a square root, you're going to get a bigger omega, but just slightly, okay? Again, so I'll show a little bit smaller increase in omega. In other words, you're going to get an overall decrease in, what are we solving for? Oh, Vmax. And if you use energy, it may be easier to see. So maybe check out the key there. Look at the energy statement. You'll have less kinetic energy available, and so there's going to be a smaller max speed. Nothing was constant in the Vmax equals A omega. And then D solved for frequency. And so how does frequency change if mass changes? Well, look at omega. And so we already said the relationship there. And so if I have a smaller mass, we're going to have a larger omega, slightly. But frequency has a direct relationship with omega, so we'll get a slight increase. So F equals that omega over 2 pi, a direct relationship. Good on page 3. Questions before we move on to page 4? Yes, little f, frequency. Okay, page 4, we get a little break from springs, head back to pendulums. So these are the big 2 items. Next class, we'll see an example with simple harmonic motion where it's not a spring and not a pendulum. So about 90% of the problems you'll see with simple harmonic are a spring or pendulum. That's kind of classic, but it doesn't have to be. And was it this class that someone talked about the half pipe snowboarding? Okay, that was a good example too, okay? All right, page 4, a grandfather clock is designed so that the arm makes 20 oscillations per minute. 20 oscillations per minute. How does that set with you? Anything running through your head? Seconds, okay? We like minutes. We think everyday life in minutes, but it's not SI. And so 1 minute, this is like saying 20 oscillations per 60 seconds, right? Seconds is where we want to be. Assume that the arm can be treated like a simple pendulum with a bob, that's just the mass at the end of a string. So maybe it's a super skinny, thin rod with most of the mass there at the end. And it's 0.4 kilograms. And again, kilograms is good. It's the only SI unit with a prefix. What is the length of the arm? So it's a pendulum, length. Hopefully our new equation from last time is running through your head. So first question, does mass matter? Not in this equation. But did they give me the period? Is the period 60 seconds? Define period. It's how many seconds, how many oscillations? One. So it's how many seconds for one oscillation. They told us 60 seconds for 20 oscillations. And so we just have to reduce it, right? And so maybe it happens too quickly to get the time of one, but doing the proportion, we know the period is 3 seconds. So it's just a different way of giving it to us. And now we're solving for L. What is the length? Again, before we plug numbers in, let's do it with variables. And so isolating L, what's the algebra? What can we do first? Uh-oh. I got to do what with 2 pi? Divide both sides by 2 pi. Again, think of it as a grouping. 2 pi, 6.28, and that equals square root L over G. Next step, square both sides, square everything, including the parentheses piece, and we're left with T squared divided by 4 pi squared equals L over G. Last step, multiply both sides by G, and we get G times period squared over 4 pi squared equals L. So if it was a variable question, that would be your answer. Now we can plug in numbers. I'm going to go gravity is 10. Now we know the period, don't forget to square, divided by that 4 pi squared. Maybe you have to use parentheses. Test the calculator you're using to see, do I need parentheses or do I not? And again, I got low battery, so y'all help me. It could go out anytime. So 90 divided by parentheses, oopsies, 4 pi squared in parentheses. 2.28. Yes, okay. So that's the length of our pendulum in the grandfather clock. Good? Okay. B, if the maximum speed is given to us as 2 meters per second, to what angle does it rise? And it says, we want the angle with the vertical. Y'all, this is old stuff at this point, right? So it's back to energy. So this is what we did in January. So kind of old, kind of new. So we'll go through and walk through it again. AP loves energy, okay? And so here we are at our highest point. Here we are at our lowest point. Where do we get max speed? Lowest point. And so V max is here. And what special place is the straight up and down of a pendulum? What do we call that special place? Equilibrium. Okay. At the high point, what's the speed? Uh-oh. It's swinging. It comes to a split second stop at the high point. But it does have height, right? And so we can say, well, at the lowest point, height equals 0. But then we have a max height. This is all old stuff. Should sound familiar. And what do they want? They want the angle that the string makes with the vertical, okay? So this is a two-stepper at least, okay? We've got energy at work, and angles mean we have to do some trig. And so if we know the max speed, to get the angle, We know the length of the string now is 2.28, right? And it's actually 2.28 in both situations. I'm going to switch colors. Remember that the height is part of the length. And so we've got this h, and then I'm going to call it a y value there. To find theta, we need the y value first, yes?
Yes.
So let's use energy to solve for height, and then we'll use trig to find the angle. And so that kinetic energy, max, at some point is all going to convert to gravitational potential. I'm going to go somewhat quick since we've already done this before. So 1/2 mv squared equals mgh. What do you notice happens? Mass cancels. And so to solve for that h, we just divide both sides by g. So you can write it as 1/2 v squared divided by g, or this should be equivalent. And they gave us the velocity max 2 squared divided by 2 times 10, 4/20. What is that max height? Uh-oh. Yeah. 0.2 should be meters. Not our final answer. That's going to help us get the angle. And so now we know that this h above the lowest point is 0.2. The length of the string is 2.28. How do I find the y value? Minus the height. And so that 2.28 minus 0.2, our y value is going to be 2.08. Now we should easily be able to find theta using what trig function? Hopefully you see a right triangle.
Yeah.
Notice the y component, or whatever I've labeled y, is the adjacent side. The length of the string is the hypotenuse, so we're going to use cosine. And to solve for theta, it's inverse cosine, our adjacent 2.08 over hypotenuse 2.28. Make sure you're in degree mode. What do we get? I get 24.2 degrees, and we're not going to lose any sleep that it's slightly over 20, right? Don't lose sleep. Go with it. Okay. It's just a smidge over 20, right? Ish. It's 20-ish. Okay. See, actually, it looks like one question. It's got 3 questions. Now, what if the bob, the mass on the end of that stick or string, is twice the mass? So now we have twice as much mass, but the same period. First question, what's the new length? How long would this new pendulum need to be? It's going to be the same. Y'all may say trick question, but we're testing. Do you know what the length depends on? It depends on period, not mass. And so if it has the same period, it has the same length. Okay, it does not depend on the mass. And gravity, yeah. No new planets or beings right here. Assume always on Earth unless told otherwise. The second question hidden in here, how would this double mass affect the max speed? And so the new max speed, well, we solved for that in part B. What happened to mass? It canceled. So if you double the mass, you double both energies, you get the same height change. Same height change. And so you get the same V max. Mass canceled. And then 3, I'm not going to necessarily solve for it, but by the way, the team met yesterday to plan out the rest of our topics to cover before the AP exam. Y'all, we're not going to have any review time before May. We normally like to have some 2 or 3 review days before May 1st. AP exams start May 2nd this year. And we're just going to have to review in May before the May 12th exam. Okay, so I know that some of the days y'all have STAR, you have A-Push, AP Lang is in there. Maybe we do self-review those days, but we're learning till the end of April, sorry, okay? So view the next 5 minutes or so as a little bit of review. They ask about tension. We haven't done tension in a while, but we do have, let's say, a ball on a string. And so if we think about the tension in the string as it passes through the max, where do we get maximum speed, maximum tension? High point or low point? At the low. So this is our max tension. And I'm going to use FT because capital T in this unit is period. So please be careful. Well, how do you solve for tension? There's not one magical equation for all. We need a force diagram. So let's draw a force diagram for the ball when it's at the lowest point. What do we got? We got gravity and tension. So it's been a while. Gravity is a straight down vector. You do not label it with a little g. That's an acceleration. You will not earn points if you label it little g on the AP exam, okay? There's like notes to graders that says no credit for, quote, little g. It has to be force of gravity, or you could do mg, or you could even do capital W, which stands for weight when it's on a force diagram. Remember, I don't like that one. FG is my favorite. And then tension is pulling what direction when it's at the low point? Up. How big do we draw tension? You think equal, because we're at equilibrium, right? And that's what we did with springs. Catch. Isn't our object making a semicircle path? Don't we have a little bit of circular motion? And if tension is up, isn't that center seeking? How do we draw center seeking forces compared to center opposing forces? Not the same. It's got to be bigger. So here's your little centripetal motion review. Center seeking forces are greater than center opposing. Now I know you're like, but with springs, you said Fs equaled Fg at that point, right? Yeah, that was true for the up and down spring or the left and right spring, but here, or no, not horizontal, but here we have circular motion at play too. And so that tension force, I'm going to go exaggerating here. It's got to be bigger than your weight because of the circular motion. Okay. To solve for tension, you can't just say, oh, mg, something, something, something. We got to do our FNet statement. And for objects moving in circular motion, remember it's FNet centripetal. So it's been a while since we've done this, so review time. How would I sum the forces? Do y'all remember? Is it up minus down? Is it right minus left? For circular motion, it's center seeking minus center opposing, because our direction towards the center is positive, away from center is negative. So I'm going to write FT minus FG, but not because of up and down. FT has to be bigger, center seeking, positive direction. And so to solve for tension, we'll add FG. Now they originally changed the mass. We need to put these two forces, F net and FG, in terms of mass. So FG equals mg. F net equals Newton's second law, ma. But wait, we're accelerating in a circular, it's centripetal acceleration. Now we don't have to, we could answer the question at this point, but again, for the sake of review, what can we plug in for centripetal acceleration? Do you remember that equation? It is on the formula chart. V squared over R. So we've got mass in 2 out of 3 forces. Does it cancel out like it did in energy? No, mass does not cancel. And lucky for us, are we increasing or decreasing? We're increasing. If we increase the mass in both terms, hopefully it's really obvious what's going to happen to the tension. It's going to increase as well. So tension will increase. FT increases. Okay. And if we factored out mass, you could actually state that tension and mass have a direct relationship. Okay. All right. A little bit more time. I want to at least get the next problem started. Page 5. It's a little different. Okay. So now we're starting to get into those left field, not cookie cutter, AP level type of questions. Okay. And so anytime you're given a graph, whether it's plotted already or you're asked to plot something about it, please read the axes. Now this one, it's teacher created, so it was a little difficult to label the axis, but notice the title, okay? In physics, your titles are written as Y versus X axis. And so on the Y-axis is your potential energy. On the X-axis is your stretch distance. It's not put there because it's X and X. It's just the independent variable. It says a 4 kilogram mass is attached to a vertical spring with an unknown spring force constant. The total potential energy in joules of the spring and gravitational are shown as a function of the spring's stretch. And they tell us joules and meters, so everybody's SI. The dashed line shows the total mechanical energy of the system. So refresh my memory about mechanical energy. Yes, it's kinetic plus potential. And here they've told us gravitation and elastic potential. So 6 joules on the graph is your total. Notice it keeps going up to 7, up to 8. Is that possible? Do we need to look at the energy above 6? No, not unless they tell us that some external force adds energy into the system. It's not, so I'm going to cross it out. So we found a limit. A, what is the max speed of the mass? Now we are going to have changes in gravitational potential energy. So this is going to be a vertical setup, by the way. Oh, they told us that, vertical spring. Where do we find max speed? So imagine we have maybe a spring attached to a ceiling and we put a mass and it's going to go up and down, up and down, up and down. Where do we find max speed? Well, not always. Sometimes that's true when potential equals 0, but not always. I'm looking for something different here. What special place do we get maximum speed for spring oscillations? At equilibrium. Okay, at equilibrium. Is equilibrium labeled on the graph? No. Is kinetic energy on the graph? No. But hopefully you remember the simulation from last time. Could we add kinetic energy to this graph? 6 always is held true, right? So in the beginning, you have 6 joules of potential. How much kinetic do you have? 0. When you have 2 joules of potential, when it crosses the y-axis, how much kinetic do we have? 4. When you have 0 potential, how much kinetic energy do we have? 6. So I'm just giving myself some points. How am I going to connect these points? By the way, they didn't tell us to do this. It's just an added visual, hopefully for help. How do we connect these points? And how does it keep going? Well, hopefully you remember it's like a mirror image curve, right? And so we'll curve symmetrically like so. So where do we get maximum speed? It's when we have maximum kinetic energy, and that happens at the point 1 location. Guess what's true? What special place is at that point 1 stretch? Equilibrium. So we've identified the equilibrium on the graph using energy knowledge. Yes? Okay, so we'll pick up with this one next class. We only have one more class. We're going to do this page and at least 2 others. No way are we going to be able to do, 14 pages in one class. So extra practice for you there, right?